Today we're going to learn about adding vectors. Now vectors are values that have both direction and magnitude. We can compare those to the counterparts that are scalars. Scalars have only magnitude. Magnitude is the size. So for instance, we could say that this ball has a mass of 10 grams. Grams don't have a direction. 10 grams, there's no direction involved. That's just a magnitude. So that's a scalar. On the other hand, we could say the trip from the Ortner Center to the Kruger Center is, I'm just making up a number here, 300 meters, but it also has a direction. That's 300 meters southeast, if I have my directions right. So we have a direction and we have a magnitude, and that makes it a vector. Now with vectors, we could have a one-dimensional vector, or a two-dimensional vector, or a three-dimensional vector. We live in 3 dimensions of space. 3 dimensions is going to mean you have 3 mutually perpendicular directions, such as up, down, left, right, and forward, backward. So these would be 3 dimensions. This would be the first, the second, and the third. If you have one-dimensional motion or one-dimensional system, you only have one of those 3. So generally, especially for drawing, we will just use for one-dimensional the left-right option. We'll just use the one that was my second here. And oftentimes we will use a positive sign to mean to the right and a negative sign to mean to the left. So we, in a one-dimensional vector, can give our direction just by using a plus or minus sign. Now, when I was in grade school, my teachers, of course, taught us how to add and subtract. And they taught us to do things like this. If I have 3 plus 5, I'm going to use the number line. And so first I start at 0, or the origin, as we have learned to call it as higher level students. And I go, since that's positive, I'm going to go to the right that number of units, so I'm going to go to the right 3. So I'm going to go 3 to the right. And then I have plus 5, so I start at the end of the first one, and I'm going to go, since it's positive, to the right again, 5. So I go from here to here. So this was 3, and this was 5. And then to get my answer, I just start at the beginning, at the origin, and go to the end. So I have 1, 2, 3, 4, 5, 6, 7, 8. And I get 3 plus 5 equals 8. Now, that was not very highly sophisticated, but that's how my teachers taught us to add when I was in grade school. Now, what if instead of doing 3 plus 5, I had been asked to subtract? So let's say that my teacher gave me 3 minus 5. Well, I start by first putting that 3 on there, just like I did before. But then this is a minus 5, and minus means to the left. So I'm going to start at the end of the first one, and then go to the left. So I'm going to put this a little bit below so I'm not on top of it. Go to the left, 5. And so here was my 3, and here is my minus 5. And what I really did is I just subtracted, meaning adding a negative value. So this is 3 plus a negative 5. I could have written this more explicit to the way I did it. 3 plus minus 5. And then once again, I start here, count to the end. I had to go to the left 1, 2. And so what we call the resultant, and actually I didn't write in the resultant last time, I should have. Here's the resultant, the answer from my addition was minus 2. So that's how my teachers taught me to add when I was in grade school. So, what does this have to do with vectors? that is exactly how we add vectors. This is showing the graphical addition of a one-dimensional vector. So what we have here is graphical addition. Now, what if we, instead of having a one-dimensional vector, we have a two-dimensional vector? Two-dimensional vector, we'll have here a two-dimensional vector that has, two-dimensional vector that has left-right as one dimension and up-down as the other. Now notice I have labeled X for the horizontal or left-right and Y for the vertical or up-down. Now things can be a little more complicated. For instance, let us say that I want to add, well, I actually need to start with something more basic. How do I plot a vector on here? Let's say I have a vector that is a vector. This arrow on the top means it's a vector. Now in a textbook, instead of using an arrow, they might make it bold. But indicating bold letters when you're writing is virtually impossible for most of us. So by convention, we just put an arrow above a vector to indicate that it's a vector. Now A is equal to, and I'm going to have two components, two pieces. And I'm going to make this easy. I'm going to make it 3x hat plus 2y hat. What does that mean? That means that it's 3 in the direction of x. This x hat we call a unit vector. Some places you'll see it written as an I hat. I hat and x hat mean the same thing. They mean a unit vector. Unit is 1, so it's a distance of 1 in the direction of x. Whether it's I hat or x hat, it means in the direction of x. So I have 3x hat plus 2y hat. So that means plus 2 in the y direction. Y hat is the unit vector for y. So now I can plot this, and I'm going to try to do this a little more carefully. So I start here at the origin, and I want to go over 3 and up 2. Now using the boxes here, I can see that I'm doing it right. Whoops. Almost right. I am somewhat a perfectionist, so let's do that again. 3 and 2. Alright, so there is my A vector. Now I'm going to have a B vector, and I will make it minus 2x plus 4y. Got to remember to put the hats on there so it's unit vectors. So now if I want to plot this, it's going to go to the left 2 and up 4. So I, just like before, I start at the end of the first one, then I go back 2 because it was minus 2, and I need to go up 4. And so there I've plotted B. So we have the vector B here, we have the vector A here, and the resultant is the answer that I get when I put those together. So the resultant is going to be the vector that starts here and ends there. Now I need to get this resultant in some kind of reasonable units. So I can look at this. How do I determine? Well, one thing I could do is I could get out a ruler. If I measure the distance from here to, let's say, here, and that's 5, and I would measure this, and that's, let's say, 1, I'm in the wrong. Let's say that is 1 inch equals 5 units, whatever the units happen to be in this. Then I can measure the length of this, and when I have that length, I will just have to use this conversion factor of 5 units per 1 inch. Right, that's equal to 1, so that's going to be my conversion factor. So I measure this length in inches, and that will give me how big it is. Now, I didn't measure out this. I don't know that it's 5 inches out or 1 inch out here to 5. So measuring with a ruler is not going to be very useful. Furthermore, you won't be able to see me doing it. But let's go ahead and figure out another way we could add this up. One would be to actually look here. How far over does this go to the left? How much does it go up? And as you saw when I wrote it, it makes a box when I put the vector on. And that box showed us that our resultant was a vector plus b vector equals 1 x hat, that is 1 over 1 going from here to here, and plus 6 y hat. Now I could have also done this instead of showing it graphically and measuring carefully. I could have done it algebraically to get the same result. Notice I have these lined up above each other. If I add them, then I'm going to have, in the x direction, I have 3 minus 2. 3 minus 2 is 1. In the y direction, I have 2 plus 4. 2 plus 4 is 6. By the way, I had I hat. The corresponding is j hat for the y direction if you're using that. And if you were using a three-dimensional vector, it would be k hat in the place of z hat. So I can add them graphically by plotting these out here, drawing the resultant. I can add them by components by adding the x values separately and the y values separately. Going back to what good old Mrs. Berg taught me when I was in math in high school, apples and oranges can't be added. So you think of the x's as apples and the y's as oranges, and you only add the x's together, you only add the y's together. So I have a resultant here. We call this answer the resultant. But oftentimes we want to know the magnitude. Remember, magnitude means how big a value is, and the direction of our vector. So if I want the magnitude and direction, I'm going to have to convert this into magnitude and direction. How do I do that? Using our good old trigonometry skills. First of all, note that it is required that the dimensions that we use, our x and y directions, are perpendicular to each other. You can see here they're perpendicular. So if they're perpendicular, I can take this vector and I can redraw it, and I'll just redraw it bigger. Don't have much more space here. Okay, so it was over 1 and up 6, so I'm going to go over 2 and up 12, just to 2 and up 12, 2, 4. Boy, I hope that's right. Okay, that goes over 2 and up, yeah, over 2 and up 12. I know it doesn't quite match up with my grid. So if I take this and break it into components, I have actually a right triangle with an origin, and I can plot out my two components, as we call them. There's one, there's the other, and this is a right angle. Now we've learned some rules along the way. We have learned things like the Pythagorean Theorem and trigonometry functions, sine, cosine, and tangent. Now I'm actually going to take this and copy it to another page so I have more room to work. So copy that. Might as well go to the top of the page, it only makes sense. So here we have it. Now let's remember what these words are, the Pythagorean Theorem and the trigonometric definition. So Pythagorean Theorem. And if I spell these wrong, I will be forever embarrassed, and yet it won't matter for your learning. The Pythagorean Theorem says that if you have a right triangle, then if you label, actually it should be lowercase if you want to do this right, and if I really want to do this right, I'm going to go to a different layer. If I label this A, this B, and this C, it's very, very important that we have C as the hypotenuse. The hypotenuse is the longest line in a right triangle, the longest side. It's also the side that is opposite to the right angle. So here's the right angle. The side that does not touch that right angle is the hypotenuse. The Pythagorean Theorem says a squared plus b squared equals c squared. So given our problem here, we had a equals 1 and b equals 6. Remember, I just exaggerated this figure so all of the squares are accounting for 1/2. Then to find c, I just say 1 quantity squared plus 6 quantity squared is equal to c squared. Multiplying this out, 6 squared is 36. 1 plus 36 equals 37 is equal to c squared. Now if I want to find c, I simply say, well, c is equal to the square root of 37, and I call up my nifty calculator, and the square root of 37 is 6.08. Now, in terms of significant digits, how many significant digits do I have? I did not specify how many significant digits I had for these. Using our standard rules, they would have been 1 significant digit, and I would say, oh, well, that's 6 to 1 significant digit. I kept 3 digits here for illustrative purposes. Everyone knows that you don't have two sides of a right, well, the hypotenuse cannot be equal to either of the sides of the right triangle. It has to be larger than the other two sides. So if I put 6 here for c, it would look misleading. But that's how we find the magnitude of our resultant, or the magnitude of any vector. Now for the next part, I need an angle, a direction. Traditionally, we measure the angle like this. And I'll call this angle theta. That's the lowercase Greek letter th, theta. And to find that, I'm going to need to use trigonometric identities. So let's look at our trigonometric identities to make sure that we know them. Sine is equal to opposite over hypotenuse. Cosine equals adjacent over hypotenuse. And tangent equals opposite over adjacent. Now, something I didn't write is you really need to have angles. Sine is a function, but you need to have the angle. So it needs to be sine theta, cosine theta, and tangent theta equals opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. How do I identify which side is opposite? If this is the angle theta, right, I have theta there, then the opposite side is the side that's not making part of that angle. So the angle theta is the angle between side A and side C, hence B is my opposite side. So in my triangle here, the opposite side is B. The hypotenuse we've already established is the long side, the one that's opposite the right angle. So, sorry, I pressed the wrong button. It should be coming back here. So sine theta is equal to B over C for this case. That was because I got anxious and pressed it twice. Cosine theta is adjacent over hypotenuse. The adjacent side is the side that makes theta that's not the hypotenuse. So this was the hypotenuse, A is the other side that makes theta. So cosine theta must be equal to A, the adjacent, over the hypotenuse we've already established is C. And finally, tangent theta is opposite over adjacent, which means that it's B over A. So if I want to find theta, I have exact values 6 and 1 for A and B. So that's the best one to use to find the angle. So I will use them. I will have tangent of theta equals B over A equals 6 over 1. Now I want to get theta by itself. That was tangent theta. So how do I get theta by itself? Well, I use the inverse function for tangent. The inverse function for tangent on different calculators, you'll have a different button. You can put a tan theta, or you can put tan raised to the minus 1 of theta, or some will even have inv tan. Those are all the inverse functions. What the inverse function does is it gives you, actually I shouldn't have put thetas there, I didn't put them here initially, put them there when I shouldn't have. They will give you the argument. So if I do arctangent on the left side, I have to do it on the right side. I can't just do it to one. So I will have arctangent of tangent theta is equal to arctangent of 6 over 1. So how do I get my angle? Well, remember, arctangent on tangent gives you theta because they're inverse functions. They undo each other. So the left side now is theta equals, and the right side is arctangent of 6 over 1. So now I call up my calculator, which I hope does arctangent. And in degrees, that's 80.537. Okay, I'm just going to put 80.5. And so there I have my angle. And so that's how I find my magnitude. I apparently erased there. My mistake. I didn't notice when I did it. 6.08 is what I had there. And so now I can write my full result. I had vector A plus vector B equals 1x hat plus 6y hat equals 6.08 at 80.5 degrees. Now 80.5 degrees is technically not enough, because it could be 80.5 degrees clockwise from this line here. So I have to say something to give me a direction. So I generally put y of x. That is, it's going in the direction toward the y-axis, starting at the x-axis. So here we see the complete addition. Two different ways of specifying the answer. They are both correct. The answer in coordinates, that is the components of the vector, is correct, but so is the answer in magnitude and direction. This has direction because you have the components have their individual directions. This one here we often consider more useful because knowing the actual magnitude is very useful to us. So we can add them graphically or by components. Now things can get, of course, more difficult. What if I have this for my starting vectors? I'm going to start with a vector is equal to 7.50 meters at 30.0 degrees north of east, and B vector is equal to 4.25 meters at let's make up an easy number, 55.5 degrees west of north. We have two ways of doing this, by components or graphically. If I do it graphically, and I'm going to do a quick and dirty graph here, this isn't going to be a very special graph. If I do this graphically, I'm going to get something that looks like this. Probably too many numbers there, don't you say? Well, for my purposes, that'll do. Whoops. Let's choose green. And so I have 7.50 meters at 30 degrees. So 7.50 meters at 30 degrees is going to go something like this. Oops. That's a big mistake, one that can't be overlooked. Something like that. So there's my vector A. Now, I really should change the colors on these things. So vector B, if I'm going to do tip-to-tail addition, that is, if I'm going to put the second vector at the end of the first vector, then I'm going to need to have vector B start here and go 4.25 at 55.5 degrees west of north. Now, I didn't actually specify what directions were north, south, east, west, did I? North, south, west, east. So if I'm going to draw that vector and I'm going to start at the end, I need to go 55.5 degrees west of north. So this direction is west, this direction is north. Said of north, so starting north, it's going 55.5 degrees this direction. So that vector is going something like this. So it's going to be something like this, but only 4.5 long. So there is a real quick and dirty of drawing those out. And so the resultant would be starting at the origin and ending up at the end of my second vector. Doing this graphically has definite value. I can see what's going on and it makes a little more sense to me when I draw it, but at the same time it's hard to be accurate and takes a lot of work. So I usually do this kind of addition by breaking them into components, so breaking each vector into its components and then adding those components individually, and then if I want a magnitude and direction, I do the work we just showed to reconstruct the vector in magnitude and direction. So let's go through these steps. Let's break each of these vectors into components. So my first vector was 7.50 meters at 30 degrees north of east. So here's my first vector. I want it to be a straight line for some reason. Here's my first vector, just a rough version of it. And now I'm going to put my values I have. So this is 7.50 meters. This angle here is 30.0 degrees. And now I need to break it into components. So in terms of components, I'm going to start at one end and go parallel to east. Start the other end and go parallel to north. And that makes a right triangle for me. Now with this right triangle, here's my right angle. I can break my vectors into the components by looking at which one is which. Now notice east is x, so I'm going to use x hat and y hat. X will represent east, y will represent north. If I want to find how much is in the x direction, then I actually simply say, well, which side of the triangle is the x component? The x component, or this is x like this. Keep changing my plans here. X like that, and y like this. So that means this side of the triangle is x. Now we had three names: opposite, adjacent, and hypotenuse. Clearly, 7.50 meters is the hypotenuse because it's opposite to the right angle. My 30-degree angle is made by the hypotenuse in this side, so this side here must be adjacent. So this is my x component, and this one here, opposite side, y component. So my y component is the opposite, the x component is the adjacent. Now, I know the hypotenuse, I know the angle, I want to find the adjacent. I have to look at my trigonometric functions and say which one is going to relate the adjacent side and hypotenuse. Well, clearly, cosine theta has adjacent hypotenuse. By the way, you don't have to memorize these. I will give them to you on every test, but it sure saves time to remember. And now, when I was in high school, my teacher had us memorize sine theta is equal to opposite over hypotenuse, cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. But then I have heard other mnemonics to help you remember. Like, the famous Indian SOHCAHTOA, that is S-O-H. See, I don't use these mnemonics. Ka-toa. So that's sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Or there is one that a student taught me about 8 years ago. Some old hippie came hopping through our alley. Just a way to remember these. But like I said, you don't have to memorize them. You probably will, because it saves you a lot of time and you'll use them a lot. So what we've established is cosine is going to relate the hypotenuse and my adjacent side. So I'm going to call variable A the adjacent side and variable B the opposite side to make my life easier. So I'm going to look at this and I'm going to say, okay, using cosine, I'll have cosine of 30.0 degrees equals the adjacent side, which is what I'm looking for, over the hypotenuse, which is 7.50 meters. Well, if I want to solve this for the adjacent side, just multiply across, and I have adjacent is equal to 7.50 meters times cosine of 30.0 degrees. So once again, we call up the calculator. 7.5 cosine of 30.0 degrees equals, come on, it seems to have stopped. I'll put a multiplication sign maybe. Okay, the calculator has failed me. I do have a plan B. I have another calculator. I'll try again though. There we go. 7, well, I'm not sure why it has a comma there instead of a period, but it looks to have come out correctly. 6.50 to 3 significant digits. So I'm going to go with that, 6.50. And notice I had units, meters. Now I need to find the opposite side. So to find the opposite side, I'm looking for opposite, and I have the hypotenuse. Now one could argue, wait, you know the adjacent now. Yes, I do. But I know the opposite without having any round off error. The adjacent I have round off errors, or not the opposite, the hypotenuse. So I'm going to use the hypotenuse because there's no round off error. So doing just like I did before, the trigonometric function that relates opposite and hypotenuse is going to be sine. Hence I have sine of 30.0 degrees is equal to B over 7.50 meters. Solve that for B. B is equal to 7.50 meters times sine of 30 degrees. Now sine of 30 degrees is 1/2. That's something that I'm sure we all had to memorize. So 1/2 of 7.5 is going to be 3.75 meters. So now I have the components of my A vector. Now let's do the components of the b vector. So the b vector, 4.25 meters at 55.5 degrees north of west. So I will draw 4.5 degrees north of west, or excuse me, 55 degrees north of west is something like this. And 4.50 meters, 55.0 degrees. I need to put in my component directions, so I will put in dashed lines again for my components. This time I'm putting in the north one first, and then I'll put in my east one second. And now I have a right triangle. Now if you look at this, first thing I'm going to do is identify which side is the x component, which side is the y component. Just like before, I am identifying the horizontal direction as x, the vertical direction is y, and so that means that this horizontal line is my x component, the vertical line is my y component. So I want to find my x component. Is this x the adjacent or the opposite side, I would ask. If you were in class, you would all answer that's not making part of this 55-degree angle, so it's the opposite side. So to find my x component, I'm going to once again call my x component A. Well, I won't because of obvious reasons. I will call it D, and I'll call my y component F. It's just bad form to use Z. I don't like to use Z. It stands for a number. So in this case, to find my x component, I have opposite side hypotenuse, that's sine. So sine of 55 degrees is equal to my opposite side d over my hypotenuse of 4.50 meters. Solve that for d, and I get d is equal to 4.50 meters times sine of 55.0 degrees. I'll bring up the calculator when I'm ready to do both calculations. To find the adjacent side, the y component, that's adjacent in hypotenuse, that's cosine of 55.0 degrees, is equal to f over 4.50 meters. Solving that for f is equal to 4.50 meters cosine of 55.0 degrees. Now notice here, to find the x component of the first one, I was using cosine. To find the x component of the second one, I was using sine. Why the difference? Because of where the angle was measured from. This one was measured from the y-axis. This one here was measured from the x-axis. So now I need to call up the old calculator and do these calculations. So the first one, 4.50 meters times, okay, I was too slow. One needs to not be super slow. 4.50 meters times sine of 55 degrees. Now I didn't put the 55.0 because the calculator doesn't care. So that's 3.69. Don't forget the units, that's meters. Now for the second one, I had 4.50 times cosine. So let's replace that with cosine. Uh-oh. Let's start over. 4.50 times cosine of 55. And that gives me 2.58. So now I've broken this one up into components, except for one thing. What did I do wrong? Well, I didn't make any mistakes, but D is actually negative my x component because it's going to the left. Notice that if I start here and go to here, if I add these two components, I add a plus f, but I have to do a minus d because it's going to the left rather than to the right. So if I write these two vectors down now with their components, and I'll write them at the bottom of the page, actually, make another page, and I think this will allow me to just roll it through to the next page and see both. So I'm going to put my two vectors here. So vector A, after all this work, writing it in components, it was 6.50 meters x hat plus 3.75 meters y hat. And vector B is minus 3.69 meters x hat, minus because it was going to the left, plus 2.58 meters y hat. Now if I'm going to add these up, remember we add apples and apples, oranges with oranges. So vector A plus vector B is equal to 6.5 minus 3.69. I'm pretty sure we can do that in our head, right? 50 minus 69 is going to be whoops, put the decimal in the wrong place. .81 meters x hat. Adding these together, 6.2, well, that's an 8. I wasn't careful. 6.33 meters y hat. Now that's a correct answer. It's written in components. What if I want to, as a final step, write that as a magnitude and an angle? Well, I have myself a triangle that goes over and you can tell these lines aren't perfect. It's the idea that counts. So I have here 2.81 meters, here 6.33 meters. If I want to find this angle and this magnitude, then for the magnitude I will use the Pythagorean Theorem, which says C is equal to the square root of 2.81 meters squared plus 6.33 meters squared. And for the angle, I would have tangent of theta is equal to the opposite side, 6.33 meters, over the adjacent side, 2.81 meters. So to get it from tangent to theta, I have to use arctangent. So I do arctangent on this side, and I get theta. Arctangent on this side. Notice the meters cancel, so I drop them off. So now I just need to pull up the calculator one last time, and I have C is equal to the square root of 2.81 squared plus 6.33 squared. Oh, come on. That should have worked. Calculator's not happy with me today, apparently. Okay, so 6.93 And my angle is going to be arctangent of 6.33 divided by 2.81. 66.1. Now, what was my reference point? I was measuring from east going north, so that's going to be north of east. So for my final answer then, I can write A plus B equals 2.81 meters. Now instead of x hat, my x was east, so I'm going to put east, plus 6.33 meters, and instead of y hat, I'm going to put north, and that's equal to 6.93 meters at 66.1 degrees north of east. So either one of those is a perfectly correct way of writing the answer. So once again, it depends on your problem, which way you're going to write it, but that's how we do addition of vectors. And we will spend a lot more time doing things as components than we will as graphical. But it's important to be able to do the graphical because it gives you the groundwork for how the component method works, and in some cases it is going to be easier, and it's often better for getting the initial visualization. All right, have a great day.